Mechanics of materials, free body diagrams. We are going to study free body diagrams. FBD are diagrams used to show the relative magnitude and direction of all forces acting upon an object in a given situation. A free body diagram is a special example of the vector diagrams. Now we will study vectors.
The vector shows the magnitude by the size of the arrow. Now let's start an example. Here, as you see, there is a box which has 10 kilogram and a man is pushing it on the floor with a force of 20 Newton, and the floor is rough. What does it mean? It means that it is difficult to push the box. In that case, we can easily understand that there is friction in this surface, and the friction coefficient is given us by here 0.6, and the man is pushing the box with 20 Newton force. Let's solve the problem. Let's see what kind of forces are affecting on this box, and is it possible for this man to push this box. This box has 10 kilogram of mass and he is pushing with 20 Newton, and the floor has a friction. Let's start from drawing the box and writing the forces affecting on the box. First of all, number 1, the weight of the object. Number 2, the pushing force of the man. Number 3, normal force applied by the floor. And number 4, the friction force because of the rough floor. For the weight, we can draw an arrow. Because of the gravity, of course, the weight is downwards. The weight is pulling force of the Earth's gravity, which is always downward. Next, draw an arrow that follows the direction of the pushing force. A man is applying the force. F application, remember the previous video. This is force applying on the box. And number 3, the normal force. The normal force is here, this normal force, which is against the weight load. And number 4 is the friction on the floor, which is at the opposite side of the force of man pushing the box. Force, and against it there is friction force. There is weight here, weight of the box, and there is a normal load against to this weight. So now let's understand that these forces are acting on the opposite directions. So we will see them as numbers. First, let's start to find out the weight of the box. As you know, mass was 10 kilogram and this is 9.81 gravitational force. So we can say the weight is 98.1 Newton. And remember the equilibrium. According to equilibrium, this force and this force, W and N, has same value. Which means N normal force minus W weight is 0. So N and W has same value, which is 98.1 Newton. Now how about the pushing force, the applied force? A man is pushing this box with 20 Newton. The resisting force, friction force, which has a formula, friction force is equal to coefficient of friction times N. Why? Because N is responsible of the force reacting against the gravity, against the weight. For that reason, N we already calculated as 98.1 Newton, and if you multiply with the coefficient of friction mu, the result is 58.86 Newton. So the friction force is 58.86 Newton. What was the man's pushing force? It was 20. So 20 comes here, Newton comes here, but this much, 58.86 is resisting. That means that this one is bigger and this is smaller. So the box will not move. The answer of the question is the box will not move. Let's remember the famous theories, Newton's theories. If there is a force in one direction and there is a support for this force, if this support prevents movement in any direction, in that case there is a reaction force in that direction. So this is N and W, and this is also F and here friction force. And in the same idea, if there is a force to cause moment and there is a support for this force, here if this support prevents rotation, it means that there is a momentum force as a reaction force at this point, at this support. Here let's look at the free body diagram examples. You know, this is a pole, electricity pole. There is a lamp here. This is image. This is a real case, and in our mind we have to make some concept drawing. This is the main pole, and there is a branch pole here which holds the lamp. So this lamp gives a weight to this system. So here the free body diagram is shown. There's a weight here, and because of the support there are reaction forces here. Look at the other examples. There's a crane here. This is the rotating point, which we call support. It is hanging some object, and there is a huge concrete block here, which also gives a pushing force in order to balance the crane. So in this system we have we have to show this 1 and 2 main forces, and that's it. It's enough. These are the details. The drawings can be like this or just as a line, because the important thing is the force here. Look at this huge monument, huge building here, and it's like a chair or like a table. It has, suppose that in two-dimensional we are looking, it has two legs here, and there's a weight because of the huge body, concrete body here, and the reaction forces acting on the support. You can see many different examples in our daily life. Look, there is a system, steel truss system here, and the forces are acting on different parts. No matter they are in an inclined surface or flat surface, the forces should be shown like this. But here there is an inclined surface with 45-degree. So the normal force acting here, it should be perpendicular to the surface of this inclined surface. And look at this forklift. It has several different parts with different angles, but no matter, they are all in the vertical direction, as in this toy. Vertical direction, and because of this rotating, there is a rotating force. And these are also the other examples from the machine parts. Remember, the force, normal force, is applied perpendicular, 90 degree to the surface. Here the boy is standing here. Of course, for that reason it should be vertical. But here the inclined surface, because of this inclined surface, the force should be as before, as previously I explained. This is 90 degree here, perpendicular. Look at here, there is no inclined surface, but the forces are affecting with an angle. In that case, it's not a problem. We have to show them as they are. This is 60 degree. This is 45 degree. This is 30 degree. These are the forces, external forces. But the support force, reaction force should be vertical. Why? Because this is not an inclined surface. There's a problem here. Let's solve the problem in the other video.